Hey,
Hey there, how are you doing?
I'm alright, not bad.
Good. All right. What's new?
I'm sorry?
What's new?
Oh, no, nothing much. Nothing really new.
Hmm?
Just been monkeying away and
Yep.
stuff, and what do you call putting in graduate school applications as well.
Oh, I didn't know you were doing grad school.
Because the more I keep studying this, what do you call it? I had to have a backup plan
I see.
with
Okay.
it. Um, so,
Hmm?
but yeah, so that's what I've been doing. I'm applying to the CUNY grad school for public health,
Hmm.
trying to get engaged.
Is
Uh,
that New York?
yeah.
And you said this is for masters or
Yeah,
uh,
master's in public health.
got it. It's cool.
So trying to do that.
Mhm.
In epidemiology and biostats.
Yeah.
So
Cool.
yeah. So let's see. Let's go for more chem stuff.
Okay.
Or just load it up. Mm, Okay. All right, then we dropped off at this one. And we'll be doing this till 4:30, right?
Hmm.
Okay. Sure. You guys see my screen?
Yeah.
Okay, awesome. Okay, so we have what do you call it? 17. Okay, I got this right. Yeah, contains hydroxide. Uh, okay, Bronsted-Lowry acid.
Uh-huh.
So why exactly did I get this wrong?
You tell me.
Acts as a proton donor.
So what? Yeah. Okay. So
Okay.
what do these molecules look like if you had to draw them out?
Um, okay, so CH4O. We have uh, oops, no, wrong one. How do I fix this? Oh, there you go. Okay. Oh my God. Okay. Okay. Got it. Got it. Got it. So let's see. Okay. So that's CH4, but we have O. So no. Oh wait, does that have to do with the oxygen content?
So let's just try to draw what these look like. So, so you drawn methane, and that's correct.
Uh-huh.
Now, let's think about what CH4O would look like.
Okay. Um, well, all right, so this would obviously have to go.
Good.
And then we just go right about that.
Uh-huh. Continue.
Um,
How many H's do you need?
E4. So we have three. around here.
All right.
Would I add the other H here?
Yep.
Okay. Oh, and that makes it an alcohol.
Yep.
Yeah, and then okay, this has more alcohol content because if we do C3H6, blah blah, blah, it's gonna have two.
Well, try it out.
Let's see. So C3, so 1, 2, 3. Okay, so that's 1, 2, 3. Oh, wait, no, no. Hold on. All right, so if we have, let's go and erase this then. Are you clear? Oh, wait. Okay. So C3, so I mean to have 3, 2, 3, H6. All right, H5. And then
So, what molecule do you think of when you think of an acid?
uh say it one more time.
So, what molecule do you think of when you think of an acid?
Um oh, it's a molecule that's trying to gain, I mean, trying to give away electrons, right?
Um, Tell me more.
So like, like bases are trying to gain electrons and stuff because they're uh not complete per se and whatever, so they try and take so they can complete themselves and whatever. And then acids tend are over, they want to deprotonate.
So, acids, they want to do what?
Deprotonate.
Are you sure?
Or do they want to protonate? Wait, bases want to protonate, acids want to deprotonate.
The other way around.
Oh, it's the other way around. Okay, so bases want to deprotonate. Oh, okay. Yeah, okay. Um, so that means that okay, so what do you call it? It's gonna be missing an H,
Um,
right?
so what would you get?
So if it's missing an H, we have 1, 2, 3, 4, 5, 6. Then we can have with an O here, no here. So this will make the O2, right? No. Wait.
You're close.
Yeah. Like that?
What is that thing?
It's an O. The O2.
Um, so do you remember what a carboxylic acid looked like?
Oh, okay. So you're right. Okay. Uh, so then putting the O there. Double bond it, right?
Uh-huh.
Yeah.
And what else do we need here?
Well, we have our 6 H's, our 3 C's, and our 2 O's.
Okay.
Do I need to put a minus somewhere?
Well, how many hydrogens are in this molecule?
6.
How many do you have?
6. Oh, no. Sorry. I have 7.
Uh-huh.
Yeah. So that means I need
Oh,
to.
no. It seems like you have 1, 2, 3, 4, 5.
Yeah, 6.
Uh, wait. 1, 2, 3, 4, 5, 6. Okay, okay. Um, oh, well, how many bonds can carbon make?
Oh, this has 5, so we're gonna just take out this.
Okay.
So 1, 2, 3, 4. Yeah.
Now
But
what?
this means that it has an extra H.
Yeah, so where would that go?
So we
Oh,
just
no,
do
no,
that.
no. You're,
I was right there.
yeah.
Okay.
So this is just like what you did with the alcohol.
Yeah.
Like, how many bonds can oxygen make?
Uh, 5, right?
Um,
No, no. Um, 3.
so so it's valence electrons. The number of valence electrons will be 6.
Oh, 6. Okay.
So it can make 2 bonds.
Mm-hmm.
So the way that you have it here, you have like 5 valence electrons that are free.
Okay.
But if they're free, well, they don't want to be free because they turn it. That's what a free radical is.
Mm-hmm.
So where do you think? And we need to put an H somewhere. So where do you think that H would go? Yeah.
Here. Yeah.
So so yeah, I want you to think about um so this over here,
Mm-hmm.
what I drew. Uh,
Yeah. Oh, yeah,
so,
we do the same thing.
oh, okay.
Yeah. Yeah, you just put the arrow down and put it up.
Yeah, tell me about this molecule losing a proton and what it turns into.
So if it loses a proton, it turn into that, right?
Um, yeah. Hold on one sec. I just need to do something.
Actually, no, no, no. If it loses a proton, we lose this H over here, right? And then it's ready to pretty much grab on to anything around.
So when it loses um that H,
Yeah,
it would turn into that, right? An O
yeah,
minus.
yeah.
What happens with that O minus?
Um, isn't this when it can rotate or something?
Something similar to that.
Um, it has resonance, right? Something like that.
Yeah, show
Yeah.
me how the resonance works.
Um, so resonance means it would be able to move. Would it move up here?
Sorry, my computer's getting a little messed up, but here, let me do this. Sec.
No.
Okay, so do you think you could maximize the screen?
Sure. Oh,
The window, I mean.
yeah.
Okay. Okay. Sorry about that. But, okay, sorry. So okay. For a carboxylic acid could look like this. So what we so if so the Bronsted-Lowry, so by the way, the Arrhenius
Uh-huh.
definition for acid and base is that the acid produces hydronium ion
Yeah.
and the base produces hydroxide ion.
Yeah.
The Bronsted-Lowry definition, which is the best definition, um, involves the acid being a proton donor
Yeah. And
and
then
yep,
base being a proton acceptor.
yeah. Now you could also have Lewis
Wait,
acid.
wasn't that what I was saying earlier about deprotonation and protonation?
Yeah. In I think at you were saying at first like a proton donor or something like that, but yeah, you got it. Yeah, that's what you said.
Yeah.
So there's also the Lewis definition, which is where the base is an electron pair donor
Mm-hmm.
and the acid is the electron pair acceptor.
Uh-huh.
But this definition is more for inorganic chemistry nucleophiles
Yeah.
and electrophiles.
Bronsted-Lowry is more for organic chem.
What's up?
Bronsted-Lowry is more organic,
Or
right?
well, in organic chem, you're going to be using the Lewis definitions for nucleophiles and
Yeah.
electrophiles. But generally speaking, if they talk about acidic or acidity or basicity, it's going to be the Bronsted-Lowry definition.
Ah, okay.
So, okay, so I drew the carboxylic acid here on the left, and when it loses its proton, it will look like this, right?
Mm-hmm.
Okay. Now, which form is more stable?
Uh, well, which one of these two?
Yeah.
What the hell? These two, right? That you're talking about?
Yep.
Well, wouldn't this be the more stable form?
You tell me.
Uh, oh,
So if it was more stable when it is in its protonated form, why would it be an acid then? Why would it like to donate its proton?
yeah, yeah. So no, this is the more stable form.
Uh-huh. So now let's think about why, right? So you
Mm-hmm.
mentioned resonance, right?
Yeah.
So what you'll have is electrons from this negative charge go and create a double bond here, and electrons from this double bond here go up to the oxygen to
Yeah.
produce this. And resonance means that both of these structures exist simultaneously. It's not like it's going back and forth between the two. Um,
Yeah, it's just like it will exist as such and be taken up
yeah.
either way.
So, and resonance causes electrons to be delocalized because if you
Yeah.
just had like, yeah, if you just had, um, an electron here and here, it like would be, I don't know where my zoom annotate thing went. One sec. Do you mind stopping your screen share for a sec?
Yeah. You want me to share it again?
One sec. Let me just make sure I can. All right, you can share again.
All right, you can see.
Let's see, but it's okay. Do you mind me stopping the session and then restarting it
Yeah, sure.
like in like a minute or something? So I'll
Yeah.
be back.
All right, let's
All
see if
right.
it.
Yep.
All
Okay.
right, check it.
Back. Yeah, thanks. So okay. So yeah, the uh the deprotonated form of the carboxylic acid is called the conjugate base,
Mm-hmm.
and that's going to be stabilized. So that's going to be our Bronsted-Lowry acid.
Mm-hmm.
What do you think D would look like? The structure for D.
Uh, Basically the same thing we just did,
What?
but oh wait, hold on. No, no. Just that, right?
Yeah, and um, yep, that's an aldehyde, right?
Yeah.
Good. So yeah, being able to write out molecular, you know, molecules is super important for the test.
Okay.
Okay. All right, we can. Now
Carbocation.
they're so yeah, so now they're talking about the Lewis definitions.
Yeah, I didn't know that one.
Yeah. So
Well, carbocations.
I just covered that myself.
Yeah,
So what's a carbocation?
carbocation. Oh, carbocation. Well, that's what probably a is it a carboxylic acid with one too many uh H's?
Um, you're on the right track. So we know it contains carbon. We know that it's a cation.
Mm-hmm.
So what charge do you think a carbocation would have?
Positive.
Good. So, okay, now what did I tell you about like what's a Lewis base?
Lewis base is a um proton donor, right?
Um, that would be Bronsted-Lowry acid,
Uh
but so yeah, try
oh,
again.
oopsie. What the hell? Can you cover that again? I'm not forgetting. Okay, never mind. I got it. Never mind. There you
Hmm.
go. Bronsted-Lowry acid. No, sorry. Proton acceptor, right?
So that's a Bronsted-Lowry stuff, but Lewis definitions are used in organic chemistry to indicate nucleophiles and electrophiles.
Mm-hmm.
So I just drew this hydroxyl group
Mm-hmm.
that um, is going to be the most common nucleophile you'll see on this test.
Uh-huh.
I want you to train your mind to see, like, whenever you see a hydroxyl group, to think nucleophile.
Okay.
Um, and a nucleophile means, well, nuclei have what charge?
Uh Negative?
What's in a nucleus?
Oh wait, no, nucleus it's neutral. Sorry.
What's in a nucleus?
Yeah.
Yeah, what's inside of a nucleus?
Protons and neutrons.
So,
Also positive.
mhm.
Mhm.
So nuclei are positive, so nucleophiles will attack or form bonds with things that are positive or at least partial positive,
Yeah.
right? And an electrophile will be something that has a lone pair donated to it. So and the most common electrophile you'll see will be a carbonyl group like this. So what happens is we have two lone pairs for the OH, right? And for the carbonyl here, we have down here a partial positive charge and a partial negative charge.
Mm-hmm.
So what happens is this will attack that, pushing that over to that.
Got it.
So so which one is the nucleophile here?
Uh
Uh-huh.
Here. This thing.
The hydroxyl group, right?
Yeah.
And is that a Lewis base or a Lewis acid?
Lewis acid.
So what's the definition for a Lewis acid?
Proton donor.
So all the proton stuff is Bronsted-Lowry stuff.
Oh, sorry. So then uh
What is
it's a nucleophile.
Yeah, how do you know?
Because what do you call it? It's positively charged.
Oh wait, which molecule are you talking about?
Wait, you're talking about the hydroxyl, right?
Yeah.
So, oh, because it nucleophilically attacks this.
Yeah, and you can see how I drew the electron pair there,
Mm-hmm.
right?
Yeah,
Like over here.
yeah,
So that electron pair is donated to the carbonyl carbon of the uh, molecule on the right.
got it.
Okay, so think about, so yeah, make sure you write this in your notes that um, hydroxyl is the common um, most common nucleophile,
Mm-hmm.
and the carbonyl group that can include like ketones, aldehydes, etc.,
Mm-hmm.
are the most common electrophiles. And electrophiles are Lewis acids.
Okay. Most common electrophiles are Lewis acids. Okay.
Yeah, and I should say that so this turns into this. Wait. So this turns into this,
Mm-hmm.
right? You can see everything that's attached,
Yeah.
but the oxygen doesn't want to have a negative charge there. It wants to spread it out. So it's going to reform the double bond, and carbon can only bind to four things. So something has to leave. So what I wrote as Lg, that stands for leaving group.
Yeah.
This gets plucked off. And then you would get like this.
Yeah.
Okay. So you could see, so yeah, that's like the most common type of mechanism that you'll see.
Okay.
But I want you to try, let's try this. And let's say we add like hydroxide ion to this. What'll happen?
Um, if we add a hydroxide ion to this,
Yep.
uh, when this turn into a double bond.
So tell me what happens like in terms of pushing arrows.
So when this nucleophilically attack over
Yep.
here,
Where's that?
you said we're adding a hydroxide ion into this.
Yeah, where is it attacking?
Over here, do you see my drawing?
Yeah. It seems like it's on the okay,
Yeah, this
so
guy.
in the drawing, okay. In the drawing that it made above, where does it attack?
Oh, it attacks the double bond. Hold on. So I can attack here.
Good.
Okay.
And then it'll push that double bond over to the oxygen, right?
Yeah.
So like that.
Yeah.
But then when it reforms the double bond,
Yeah.
it kicks off this
Yeah.
bond as a leaving group.
Yeah.
So this would look like so this would look something like this, right?
Yeah.
So this is I went over this problem like a few days ago with a student. It's from like an actual, MCAT practice test.
Yeah.
Um, and they don't teach you necessarily like what specifically happens here, but I want you to see that from our knowledge up here of hydroxyls being nucleophiles and carbonyl carbons becoming electrophiles, means that it can attack and then it'll form, negatively charged oxygen, which then comes back to reform the double bond and it kicks off the leaving group. It's the same
Okay.
thing in this molecule here. So you attack the carbonyl carbon, except the leaving group this time is part of its ring, so you get an opened ring.
Yeah.
So okay, so now a carbocation, right? That's going to be carbon, like hydrocarbon with a positive charge. So if we ask ourselves, what that would look like, well, what if we had something like, let's say, oh, they're talking about water. Okay, so let me do that. Oops. So let's say we had some alcohol like this, and let's say we add water. What should happen?
Um, when a hydronium ion be formed here?
That can happen.
Yeah.
So, okay, so something that can happen is the OH group can get protonated to be OH2 plus,
Mm-hmm.
which is a leaving group. So this thing leaves,
Mm-hmm.
right? Maybe I should have said, let me add an acid
Mm-hmm.
for that to happen. So when it leaves, you would be left with that, right?
Yeah.
Just that carbon skeleton with the positive charge.
Yeah.
So yeah, so this is the carbocation,
Got it.
and it's particularly secondary carbocation. If it was just like this, it'll be primary. If it was like this, it'll be tertiary.
Yeah.
Which ones do you think are the most stable?
Uh, Probably the tertiary structures.
All right, why?
Um, what do you call it? Well, primary structure is all amino acids and stuff. The tertiary is.
Oh, you're thinking about something else with amino acids.
Oh, okay.
This is prime. So primary means that you have that you have the charge on just a signal carbon,
Yeah.
and then secondary it's on these two carbons, tertiary on these three.
Yeah.
So something I was going to say or draw earlier was if we had this, compared to this, right, with a resonance,
Mm-hmm.
if we think about that in terms of electron orbitals, for the molecule on the left, you'll see electrons here and here. Okay.
Yeah.
However, with resonance, it includes the carbonyl carbon as well. So the charge is spread out over a wider area.
Okay.
So what this means is so anytime you have a charge that's spread out over, some area, it's going to be more stable. And
Yeah. Continue.
yeah,
Sorry.
it'll be more stable than if it was just um you know spread across something that has fewer substituents. So for instance, this for the primary over here, the positive charge is right at the end. So it's not really it's pretty localized. For
Mm-hmm.
this secondary one, it's at least spread out across two more or across two carbons. And the tertiary is spread apart over three carbons.
Uh-huh.
So in order of stability, it'll be tertiary followed by secondary followed by primary. And
Okay.
this is super important because you'll learn like SN1 and SN2 reactions where SN1 would favor like the tertiary structures. Um, so in this question STEM, they're asking about water with a carbocation. So let's draw maybe a secondary carbocation plus water, right?
Mm-hmm.
So since we have a full-fledged charge, whoops, over here for the the positive charge there,
Mm-hmm.
what do you think will happen?
Um, we'll get the carbon skeleton and then a hydronium ion.
So think about it in terms of like, so everything that we've been doing so far. So Orgo is all about these arrow things.
Yeah.
So think about it in that way.
Uh, well, it would be this would be the nucleophile, right?
So tell me what a nucleophile means.
That it's positively charged going to attack.
So what's the charge of a nucleus?
Positive.
And what does phile mean?
Um, what do you call it? Like, okay, I'm lost.
So let's see. Um what's the word philosophy mean?
Well,
Well,
philosophy
how
is
about,
like the study of ethics. No?
so what does hydrophilic mean?
Oh, it means that it can be combined with water.
Uh-huh. So what do you think the philic part means?
Come together.
Or anything more? What's the opposite of the vile?
Uh, phobic.
Huh? So
Uh-huh.
phobic means you're like afraid of it, you don't want to go into that. Philic means what?
That you want to combine with something.
Yeah, or that you just like something,
Yeah.
right? So like kind of a bad example, but like a pedophile is someone who likes kids, right?
Yeah.
So phile means it likes something.
Yeah.
Now, a nucleophile, we have already established that a nucleus is positively charged.
Yeah.
So a nucleophile would like to attack the positively charged thing.
Oh, so this is going to act as the nucleophile over here.
Correct.
And then, what do you call it? This will turn into an OH.
Uh-huh.
Right? And then this will end up having, what do you call it? Right?
Okay, so okay, carbocation,
Mm-hmm.
um, and water. And water could be a good nucleophile because it has that oxygen.
Mm-hmm.
Um, so tell me which one is the Lewis acid and which one is a Lewis base?
Base acid.
Yeah, and which one is a nucleophile? Which one is the electrophile? Perfect, perfect. So you could see how A says carbocations act as Lewis bases. That's not true. And then carbocations act as Lewis acids. That's true. Water acts as a nucleophile. No, it acts as a sorry. Water acts as an electrophile. No, it acts as a nucleophile. Then D, carbocations act as nucleophiles. No, they act as um, electrophiles.
Got it.
Mm-hmm.
All right, so let's clear this. Next question. pH of 2.30.
Seems like you got this one.
Yeah. Right. Yeah.
I wonder if it would be good to go over some like physics questions because I don't think we've ever worked on physics together, but maybe
Yeah.
but maybe we can, yeah, what do you think?
Yeah. See, I was doing pretty good there. Yeah. Yeah. Let me keep skipping through. What was, oh yeah. Let's find the first physics question.
Oh, yeah.
Here's a physics question.
Uh-huh.
What's the resultant vector represented as P minus Q, where P and Q are the two vectors shown below?
Okay. So do you know how to add vectors?
Um,
So yeah, don't look at
Ever so slightly.
hide the solutions.
Okay.
Okay, so what is a vector?
Well, these arrows.
Well, but what does that mean?
Like the direction something is going to go to,
Okay,
right? Yeah.
so uh so what's the difference between speed and velocity?
Um, well, let's see. Try and use some baseball physics here. The exit velocity of a ball stands for the ball itself being as fast as that.
So I think they may not make the differentiation there.
Probably not.
So
Um,
yeah, because we also have in physics, well, distance and displacement.
yeah, know about that. Okay, so isn't velocity supposed to be the speed of a certain, like the how fast a certain object can move itself, kind of thing?
How would that be different uh from velocity?
I mean, from speed.
Oh, yeah. So okay, how let me ask you this. So let's say that we have a racing track, and you start here,
Mm-hmm.
and you go through this racing track, and then you end up back here.
Mm-hmm.
So what would the distance be for this, a lap here?
The distance?
Yeah.
Oh, I don't know.
It'll just be the circumference of that circle, right?
Oh, okay. Oh, so it was as literal as I was thinking. I was just about
Yep.
to say the circumference. But
Mhm.
I would have had it here because I was gonna go like that.
Yep, yep.
Yeah.
So that would be the distance.
Yeah.
Okay. Now, um, displacement will actually be,
Oh, so like let's say we can say a car running around a racetrack is how fast it goes around, but the velocity of something like if I shoot a bullet from my gun and it ends up on, let's say, the other side of town because I just shot it up in the air and stuff, then
so
that's the velocity of where it ended up.
so before that, um, just see that the distance for this is the circumference of the track, but
Hmm.
the displacement will be 0.
Okay.
So how could it be 0, right? Well,
Well, it
uh,
never started and ended somewhere different.
um,
It
sure.
started and stopped and it started and ended at the same place. So it never was technically displaced.
Yep. So but let's think of that in terms of vectors, right? So like, first you're going up like this,
Mhm.
and then you're going to the right like this,
Yeah.
down like this, left like this, and then the rest of it going up like that.
Yeah.
So these are vectors. A vector,
Mhm.
unlike,
Oh.
yeah.
Okay, so now I think I'm understanding.
So if we added, or,
Well, yeah, up would mean we add, right?
so
And
this
then,
this rightward vector would
uh-huh.
be canceled out by this leftward vector,
Yeah.
and then this upward vector will be canceled out by the downward vector.
Hmm.
So the difference between these values here are that there are scalars and vectors. A scalar is only going to have a magnitude, whereas a vector is going to have a magnitude and a direction.
Got it.
Okay. So speed and velocity. Oh, and another thing, we how can we express, vectors in different directions? Well, we can use positive and negative signs.
Hmm.
Like, for instance, going up here, I could say is positive. To the right, I could say is positive. Down is
P
negative.
minus,
Left
yeah.
is negative.
So if we're gonna go
Right.
P minus Q, we can keep P the way it is, but then we have to make Q this way.
Yeah, yeah.
And then to finish out the vector, right, we would just have something else like that.
So yeah, but
Oh,
before
no.
we get to that, I just want to show you really quick that means since the positive and negative means that velocity could be negative, which means it's in the other direction, but speed is always going to be positive. But what I wanted to show you was that so okay, yeah, we have P, we have Q. Now, you know, if it's minus Q, then we're switching this. Oh,
That would be P plus Q, right?
oh, if I added those, yeah. But so when we add vectors, what do we do?
Um, to to tap?
Sorry. Tip to
Tip to
tail.
tail. Okay.
So you could just take,
Yeah, here goes down here.
yeah. So for that, it would look like P, Q,
Yeah,
and then that would be the P plus Q, right?
yeah.
All right. Now let's do this for P minus Q. So that's really just P plus minus Q, which is in the opposite direction. So this is minus Q.
Mm-hmm.
So we can have P there and Q here, right? And so this would be
Oh, yeah, and then that's where it technically wouldn't be correct.
that's when technically what?
Wouldn't be correct because it's not tip to tail.
Oh, no. When you're adding the vectors, that's when you do tip to tail.
Oh, when you're subtracting your.
Well, you're just think of it as addition,
Mhm.
except if you're changing the sign, you're changing its orientation. So, like, just like this is P plus Q, this, so I'll actually write that P minus Q for that one.
Yeah.
So you can see that this is P, and at the tip of P, I put the tail of Q.
Yeah.
So, and then you connect the tail of P to the tip of Q to get your resultant vector.
Yeah. So wait, why would it, if this is P minus Q, then why is it this way?
Oh,
That's
because
the correct answer.
because this is the minus Q, right?
Mm-hmm.
This is the positive P.
Mm-hmm.
So take the tip of one and put it at the tail of the other.
Mm-hmm.
So P and then minus Q, right? And then you just connect this to this to get the resultant vector.
Got it.
Mhm.
Okay. All right then. Cool.
Mhm.
All right. I'm gonna have to stop this here. Something for work is coming up. I
Okay.
just know. So, yeah, I gotta do that.
Okay.
All
Got it.
right.
So
Um,
yeah, why don't you continue working on this, particularly
yes.
the physics stuff?
Yeah.
Do you want me to put you in for
Uh, you can put me, yeah, you can put me in for next Tuesday, the same time, 3 to 4:30. Yeah.
uh the
9, right? Is that the
yeah,
9?
yeah, the 9th of
Yeah.
Tuesday, you said 3 p.m.?
Yeah, 3 p.m. to 4:30.
Got it.
I'll make sure I clear out my schedule for work.
Uh-huh.
All right then. Perfect.
All right, awesome. Okay. Have a
All
great
right.
rest of your week. All right, take
You
care.
too.